Hi boys and girls, this is lecture 8.6. Today's review topic, rates. What does a definite integral actually do? We know that it is the limit of a sum of objects as the number of objects goes to infinity. In summing up an infinite number of objects, the definite integral functions as an accumulator. When we found areas under curves, the definite integral accumulated an infinite number of areas of rectangles. In volume problems, the definite integral accumulated an infinite number of volumes of slices or disks. In this example, we'll see the connection between the definite integral of velocity and the area under the velocity function curve. Consider a car moving at a constant velocity of 50 miles per hour. If it moves at this velocity for 2 hours, it will travel 100 miles. Let's look at this problem in terms of area. If the velocity is constant, the velocity function can be written v of t equals 50. Below is a graph of this function on the interval 0, 2. The area under v between 0 and 2 is shaded. Notice that the area under the curve, the area of the shaded rectangle, is 100. This area could also be expressed as the integral from 0 to 2 of 50 dx, which equals 50x from 0 to 2, which equals 100 minus 0, which equals 100, which of course is the area of the rectangle, and the distance traveled by the car. Thus, the definite integral accumulates distance traveled over a specific time interval. On the subject of distance, as mentioned previously, there are two types of distance traveled: total distance and net distance. If you measure the distance you travel in one day, from the time you get out of bed in the morning until the time you return to your bed at night, your net distance traveled is 0. Your total distance would be, hopefully, something other than 0. If the area under a velocity curve is above the x-axis on the entire interval, net distance and total distance will be the same. If the area under the velocity curve is partly above and partly below, you must integrate the absolute value of the velocity function to get the total distance. In summary, net distance is the integral from a to b of v of t dt. Just integrate the velocity function on the interval. But to get total distance, you'll need this integral, the integral from a to b of the absolute value of the velocity function dt. If v of t is greater than 0 on the specified interval, then net distance will equal total distance. So, given a function that describes the rate of change in a quantity, its integral over a specified interval will accumulate the amount of change. For example, if r of t describes the rate of growth of a child in inches per year from birth to age 18, the integral of r of t dt from 0 to 3 would yield the total number of inches a child grew in the first 3 years. If E of x describes the rate of electricity consumption in a 24-hour period in kilowatts per day, then the integral of E of x dx from 0 to 7 would yield the total number of kilowatts consumed in the first 7 hours. Notice that in these examples, there is no need for absolute value. For the most part, the only time you need to consider the difference between net and total change in a quantity is when dealing with distance problems. It would make little sense for a function that describes a rate of growth in the height of a child, electricity consumption, oil production, etc., to go negative. The rate of change in these quantities may drop to 0, but a negative rate of growth in such quantities would not make any sense. In general, if we integrate a rate of change, we will get the total amount of change, except for distance problems, which may involve either net or total change. Here's an example from the 2009 exam. It's on the Calculator Aloud section of the exam. The rate at which people enter an auditorium for a rock concert is modeled by the function r, given by R of t equals 1380 t squared minus 675 t cubed for 0 less than or equal to t less than or equal to 2 hours. R of t is measured in people per hour. No one is in the auditorium at time t equals 0 when the doors open. The doors close and the concert begins at time t equals 2. Letter A asks, how many people are in the auditorium when the concert begins? Well, we're given a rate function. We know that integrating this rate function will give us the quantity of people in the auditorium, and we're interested in the interval from 0 to 2. So integrating our rate function from 0 to 2, 1380 t squared minus 675 t cubed dt will give us our answer. After 2 hours, 980 people are in the auditorium. And that's the answer to letter A. Letter B, find the time when the rate at which people enter the auditorium is a maximum and justify your answer. We'll know when the rate is a maximum by taking the derivative of the rate function and setting it equal to 0. So let's find r prime of t. R prime of t is equal to 2760t minus 2025 t squared. When we set this equal to 0, we find 2 times when this function equals 0, at t equals 0 and at t equals 1.36296 hours. So the time at which the rate was a maximum could have been at the endpoints of the interval, 0 or 2, or at this critical number, 1.36296. We'll need to see what the rate is at each of these times to see when the maximum occurred. So at time 0, the rate was 0. At time 1.36296, the rate was 854.527. And at time 2, the rate was 120. Therefore, the time at which the maximum rate occurred was at 1.36296 hours. And at that time, people were entering the auditorium at about 855 people per hour. So your answer for letter B, t equals 1.363 hours. Letter C. The total wait time for all the people in the auditorium is found by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. The function W models the total wait time for all the people who enter the auditorium before time t. The derivative of W is given by W prime of t equals the quantity 2 minus t r of t. Find W of 2 minus W of 1, the total wait time for those who enter the auditorium after time t equals 1. So integrating this rate function will give us the total wait time of those who entered the auditorium between hours 1 and 2. So let's set up that integral. From 1 to 2, 2 minus t times r of t, which was this rate function, 1380 t squared minus 675 t cubed dt. The value of this integral, 387.5 hours. This represents the total wait time of those who entered the auditorium between hours 1 and 2. Letter D. On average, how long does a person wait in the auditorium for the concert to begin? Consider all people who enter the auditorium after the doors open and use the model for total wait time from part C. So now we're going to use this rate function integrated from time 0 to 2 to get the total wait time of all of the people who entered the auditorium from time t equals 0 to time t equals 2. But that's not what we're asked to find. We're asked to find on average how long does each person wait in the auditorium. So once we get that total amount of wait time, we'll divide by the number of people who entered the auditorium from time t equals 0 to time t equals 2. That will give us the average time that each person waited for the concert to begin. So let's set up this integral. 1 over 980 from 0 to 2, 2 minus t, 1380 t squared minus 675 t cubed dt. That gives us a value of 0.776 hours. That means that each person waited approximately 0.776 hours for the concert to begin. Here are the scoring guidelines for that question. Notice for letter A, 1 point was given for the integral, 1 point was given for the answer. It's important to show your integral setup even though you're using your calculator to integrate. For letter B, 3 points were given, 1 for setting r prime of t equal to 0, 1 for finding the interior critical point, 1.36296, and 1 for the answer and justification. For letter C, 1 point given for the integral, 1 point for the answer, and for letter D, 1 point for the integral, 1 point for the answer. Here's another example from the 2004 exam. This question is on the calculator allowed section of the exam. Traffic flow is defined as the rate at which cars pass through an intersection measured in cars per minute. The traffic flow at a particular intersection is modeled by the function f, defined by f of t equals 82 plus 4 sine of the quantity t over 2 for 0 less than or equal to t less than or equal to 30, where f of t is measured in cars per minute and t is measured in minutes. So once again, we have a rate function measuring cars per minute. Integrating this rate function will give us a quantity of cars passing through the intersection on a given time interval. Letter A asks, to the nearest whole number, how many cars pass through the intersection over the 30-minute period? So we'll set up our integral from 0 to 30. 82 plus 4 sine of t over 2 dt. That value is 2474 cars, which means that on the interval from t equals 0 to t equals 30, 2,474 cars pass through the intersection. Now let's look at letter B. Is the traffic flow increasing or decreasing at t equals 7? And give a reason for your answer. For this, we'll need to look at the derivative of this rate function. If the value at 7 is positive, then that means the rate is increasing. If the value at 7 is negative, that means the rate is decreasing. So first, let's find f prime of t, which is 2 cosine of t over 2. Specifically, we're interested in what's happening at t equals 7, and that value is negative 1.873. Since f prime of 7 is less than 0, traffic flow is decreasing at t equals 7. Letter C. What is the average value of the traffic flow over the time interval 10 less than or equal to t less than or equal to 15? Indicate units of measure. Since this is an average value question, we'll need to include the coefficient 1 over b minus a, which in this case will be 1 over 15 minus 10. Our integral from 10 to 15 of the rate function 82 plus 4 sine of t over 2 dt. This yields an average value of 81.6 0.899 cars per minute. So from minute 10 to 15, the average rate at which cars were passing through this intersection was 81.899 cars per minute. Now let's look at letter D. What is the average rate of change of the traffic flow over the time interval 10 less than or equal to t less than or equal to 15? Indicate units of measure. The average rate of change of the traffic flow will be calculated by looking at the difference in the rate over the difference in time. So now we're going to look at f of 15 minus f of 10 over 15 minus 10. This yields a value of 1.518 cars per minute squared. This value gives the rate at which the rate is changing during that time interval. Here are the scoring guidelines for this question. For letter A, 3 points were awarded. One for the limits or endpoints of integration, another for the integrand, and a third for the answer. For letter B, 1 point was awarded for the answer with reason. For letter C, 3 points were awarded, one for the limits or endpoints of integration, another for the integrand, and a third for the answer. For letter D, 1 point was given for the answer, and the 9th point was given for units, cars per minute in C and cars per minute squared in D. Our last example is from the 2005 exam. This question is on the Calculator Aloud section of the exam. The tide removes sand from Sandy Point Beach at a rate modeled by the function r, given by r of t equals 2 plus 5 sine of the quantity 4 pi t over 25. A pumping station adds sand to the beach at a rate modeled by the function s, given by s of t equals 15t over 1 plus 3t. Both r of t and s of t have units of cubic yards per hour, and t is measured in hours for 0 less than or equal to t less than or equal to 6. At time t equals 0, the beach contains 2,500 cubic yards of sand. So this is an initial condition that we need to remember to take into account when we're setting up our integrals. Letter A asks, how much sand will the tide remove from the beach during this 6-hour period? Indicate units of measure. Since r of t is the rate at which tide is removing sand from the beach, we'll need to integrate that rate function from 0 to 6. 2 plus 5 sine of 4 pi t over 25 dt. This yields 31.816 cubic yards of sand removed in that 6-hour period. Letter B. Write an expression for y of t, the total number of cubic yards of sand on the beach at time t. Y of t will represent the amount of sand on the beach at any time t, therefore we'll need to start with the initial amount of sand on the beach, which was 2,500 cubic yards. We'll add to that the integral of the two rate functions interacting with each other from time 0 to some time t. Since t is the upper endpoint of integration, we'll write our rate functions in terms of x. We'll start with s of x, which is the rate at which the pumping station is adding sand to the beach. We'll subtract from that r of x, which is the rate at which the tide is removing sand from the beach. The integral of the difference of these two rates will be the amount of sand added to 2,500, giving the total amount of sand on the beach at any point in time t. Letter C. Find the rate at which the total amount of sand on the beach is changing at time t equals 4. Y of t is an expression which represents the total amount of sand on the beach at any time t. Therefore, y prime of t will represent the rate at which this total amount of sand on the beach is changing. So let's find y prime of t. That will be the derivative of this expression. The derivative of 2500 is 0, and the derivative of this integral is this integrand, but with the upper endpoint of integration inserted for x. That means our expression for y prime of t will be s of t minus r of t. Now let's find y prime of 4. This will be s of 4 minus r of 4, which is negative 1.909 cubic yards per hour. Letter D. For 0 less than or equal to t less than or equal to 6, at what time t is the amount of sand on the beach a minimum? What is the minimum value, and justify your answers. Y of t is the expression representing the total amount of sand on the beach at any time t. Therefore, the derivative of this expression will yield critical numbers when set equal to 0. Therefore, we'll need to see if there are any places when y prime of t is equal to 0. That means setting this expression equal to 0. S of t minus r of t equals 0. We find that this expression is 0 when t is equal to 5.117865 hours. Extreme values can occur at critical numbers as well as at endpoints of the interval, so we'll need to find how much sand was on the beach at all of these times in order to determine the minimum amount of sand on that interval. At time 0, at time 5.117865, and at time 6, we'll evaluate y of t. At time 0, there was 2,500 cubic yards of sand on the beach. Not surprising, since that was our initial condition. At time 5.117865, there was 2492.3694 cubic yards of sand on the beach, and at time t equals 6, there was 2493.2766 cubic yards of sand on the beach. So at time 5.117865, we had the minimum amount of sand on the beach. Therefore, our answer at time t equals approximately 5.118 hours. The amount of sand on the beach at that time was approximately 2492.369 cubic yards. Here are the scoring guidelines for that question. 2 points were awarded for letter A, 1 for the correct setup of the integral, and 1 for the correct answer with units. 3 points were awarded for letter B, 1 for the correct integrand, 1 for the correct limits or endpoints of integration, and 1 for the correct answer, which was the expression for y of t. For letter C, 1 point was awarded for the correct answer. For letter D, 3 points were awarded, 1 for setting y prime of t equal to 0, 1 for getting the correct critical value, and 1 for the correct answer with justification. Tip number 6 for the AP Calculus AB exam. Do not use your calculator for anything except graphing functions, computing numerical derivatives, computing definite integrals, and solving equations. In particular, do not use it to determine max or min points, concavity, inflection points, increasing, decreasing, domain, and range. You can explore all of these with your calculator, but your solution will need to stand alone. Common student error number 6, pi. Don't forget your favorite irrational constant when calculating the volume of a solid of revolution. That's it for today's lecture. Just remember, of course you have problems. You're a mathematician. Here we have 2 students dealing with their own mathematical issues. God bless you, boys and girls.